Hello students, welcome to digital classes. Today we are going to do Newton's laws of motion. In the earlier classes we have learnt objects in motion, objects at rest, distance, displacement, speed, velocity, average velocity and equations of motion. We have seen that when an object moves from one point to another, starting with a velocity u, moving with an acceleration a, covering a distance s in the time t and reaches a final velocity v. At that time, these three equations hold good. V is equal to u plus at, s is equal to ut plus half at square, v square minus u square is equal to 2 as. Many of you wonder, if we are doing Newton's laws in this class, what Newton may have studied when he was in class 9. Observe the motion of this object. Here I have a wooden plank, I have raised the height at one end and I am going to release this battery from the top. Observe carefully. In other case, now I am going to push this battery up the plane. Again, watch it carefully. Once again. Now, let me roll this battery on a level surface. Now, I am going to slide this coin, watch it. So, children, we are studying why the objects move and how they move. Philosophers, scientists have always thought about the motion of objects. It is only the techniques in measurement and mathematics which has led to the clear understanding of motion. Around 300 BC, Aristotle, on his treatise on the heavens, argued that a constant force is necessary to keep the object in uniform motion. It took nearly 1800 years to get the clear idea of how the objects move. It was Galileo Galilei who has given a different perception. Galileo argued that objects in motion would continue to be in uniform motion on level surface unless disturbed by an external agent. Galileo had two experiments in his mind. First, he observed the motion of an object down the inclined plane. He observed that the speed of the object increases as it is rolling down. Then he also has done the experiment by rolling the object up the inclined plane. The speed of the object decreases as it is rolling up. He has done the experiment on a level surface. The speed of the object decreases slowly and eventually stops. But Galileo imagined a friction free world. But in class 8 you have learned that there exists friction between the objects when they are in relative motion. Galileo has done another experiment in which he has seen an object rolling down and rolling up. Here is the arrangement of the experiment. He released the object from a height and this object went down, increasing its speed, and again rolled up, reaching the same height. He changed the setup a little different and he has seen that the second plane was inclined, which is little longer, but the height was same at the end. Here is the arrangement. What he has observed is in 2b, the ball still was able to reach the same height even though it has travelled a greater distance on the second plane. He further increased the distance, but keeping the maximum height at the end same as the first plane. He understood that the object was still able to reach the same height. Then he got an idea and he removed the second inclination plane and just released the object as shown in the figure 2c. If this object were to reach the height as in the previous case, how far should it travel? The answer, it should reach an infinite distance. So, thereby Galileo concluded that an object in motion on a level surface has to move continuously without any break. Galileo argued that objects in motion would continue to be in uniform motion on level surface unless disturbed by an external agent. Until Isaac Newton, the ideas of motion were just explained qualitatively, but it is the genius of Isaac Newton that led to the remarkable discoveries in the ideas of motion, and with mathematics background he has developed the Newton's laws of motion. Sir Isaac Newton gave the ideas of motion a mathematical form and paved paths for scientific revolution. Hence, Newton takes a prominent place in the history of physics. And Alexander Pope has written the following for Newton: nature and its laws lay hid in the night. God said, "Let Newton be," and all was light. It is because of Newton we have the rockets, and with that we have satellites, and Newton even has given the theory of gravitation. Newton also has discovered that white light has all the constituent colors. Newton invented the first reflector telescope, and we are going to study the Newton's laws of motion, starting with the first law, which is part of inertia and which Galileo Galilei has already described. Newton has given his work in the book Mathematical Principles of Natural Philosophy. Now, let us see what Newton's first law says. Every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. That was the translation from Latin, and let us see the same law in simple words. Every object continues to remain in its state of rest or uniform motion until an external unbalanced force acts on it. Newton's first law can simply be stated that object at rest wants to be at rest, object in motion wants to be in motion. Children, let us do some activities to demonstrate Newton's first law. Here I take a stack of coins and I am going to hit the bottommost one with a ruler, and we expect the whole stack to fall down, but it does not happen. Watch it carefully. Yeah, it was very funny, right? Let us do this similar activity with a stack of coins. Here I have stack of 10 rupee coins and I am going to hit the bottommost coin with a ruler. Watch it. That was very funny, right? It is because the objects at rest would like to be at rest. All the stack of coins which were at rest, they want to be at rest, and hence they did not want to move when we tried to push them suddenly. So, it is only the bottommost coin which will move because we are directly pushing it. The others which are not directly in contact, so they would like to remain at rest. Let us do another demonstration. Here I have a bottle filled with water. Here I have paper I place a coin on top of it. Now, what do? I displace the paper. Let us see where the coin falls. Watch it. The coin falls in the bottle. When I pull the paper suddenly, the coin which was at rest would like to be at rest, and hence it fell straight into the jar. Children, let us do the same activity, but instead of a coin, let us take an egg. Here I have two eggs, one is boiled and one is not. We can do with any egg, but let us use a boiled egg. How do you identify which egg is boiled? Simple, you just have to roll it, you have to rotate it. Whichever rotates for a longer time, that is boiled egg. Whichever rotates for a longer time is a boiled egg. The raw egg will not be able to rotate because inside the white and the yolk are in liquid state, and hence they try to stop the motion. Let us do the same activity. Watch it. Egg which was at rest would like to be at rest, and hence it fell into the bottle. Children, let us do another activity of inertia of rest. Here I have a bottle filled with water. What I am going to do is, I am going to lift this bottle with this thread. Watch it. I am going to tie the neck of the bottle to the thread, and I am going to lift this bottle. Let us see. Yeah, there it is. I am able to lift this bottle with this thread, but I have done it slowly. If I do it suddenly, because of inertia of rest, this bottle is going to remain at rest, and what should happen? The thread should break. Watch it. I am going to pull it suddenly. The thread has broken. Let us do another activity. I take the same bottle because I like it very much. Here I placed the bottle on a paper, and I am going to pull this. Because of friction, I am able to pull this. Now watch. This bottle is almost towards the edge. Children, you can guess, the bottle is at rest and it has to remain at rest. Watch it. Watch it. So, you have seen the object, that is the bottle, which is very heavy and it has inertia, it was at rest, and when we pull the paper suddenly, this bottle was at rest, it remained at rest. You can do this activity, but see that you do not break any object at home. Let us do another activity. Here I have two objects which are identical. Here I have two objects and I am going to move them using the ruler. Watch it. Yeah. Now, how about this one? Clearly, it was little difficult and you can also understand. Let us do this once again. Using the same ruler, at once I am going to hit both the objects, thereby applying the same force. Let us see what is going to happen. Watch it. You have seen that this object has moved farther, whereas this object moved a little distance. This is because this is more heavy. I put some rice grains in it, whereas this one is empty, it is empty box. So, the heavier object had greater inertia, whereas the lighter object had lesser inertia. So, we can say mass as measure of inertia. So, greater the mass, greater is the inertia. So, lesser the mass, lesser is the inertia. So, we can define mass as measure of inertia. Children, so what we have discussed is Newton's first law, which says an object at rest would like to be at rest. An object in motion would continue to be in motion unless acted upon by an external force. We should remember that the object in motion, the motion has to be uniform. That means its direction and speed both must be equal. So, we have seen variety of demonstrations in which we have seen the objects at rest tend to be at rest. We have demonstrations for objects in motion to continue to be in motion. This you have experienced in day to day life. If you are getting down from a moving bus, you continue to run with the bus. This is because of inertia of motion. Not only that, you see the vehicles which carry goods, all the goods will be placed at the beginning of the vehicle, so that whenever brakes are applied, the goods will not move further. Also, the goods will be tied, so that whenever brakes are applied, the goods do not fall off. Now, let us move to Newton's second law. To understand Newton's second law, we have to introduce a concept called momentum. Momentum is a physical quantity. It took nearly 150 years to understand the difference between momentum and kinetic energy, because both the quantities are related to motion. Whenever an object is moving, it possesses kinetic energy as well as momentum. Now, let us demonstrate another activity. Here I have kept all the coins in a straight line, and then I am going to hold all these coins tight to the table, and to maintain the straight line I take help of a ruler, and I will leave the last coin free to move. Now, what I am going to do? I am going to hit the first coin with another one. Let us see what is going to happen. How did that move? Watch it. Children, momentum is a vector quantity and it has direction, and I am going to demonstrate it by another activity. It will be similar one. Now, watch it carefully. I am going to take a metal ruler and I place a coin here and another coin to the side. Now, I hold this metal ruler tightly and I am going to hit from this side. This is going to move this way. So, the momentum should be transferred in this way. So, only this coin should be disturbed, whereas this coin should remain at rest. This motion is going in this way. So, the momentum has to be transferred in this direction only, whereas this coin will remain at rest. Watch it. So, the momentum is transferred along this direction only. When we have two coins placed together, but only one coin is disturbed because the momentum in that direction only is transferred. So, momentum is a vector. Momentum is the product of mass and velocity. SI unit is kg meter per second. Momentum and kinetic energy are transferred in a collision, but it is only momentum that is conserved. Newton's second law. The rate of change in momentum of an object is directly proportional to the external unbalanced force and is in the direction of the force. The same law can also be stated as the vector sum of forces F on an object is equal to the mass m of that object multiplied by the acceleration a of the object. Thereby, we get F is equal to mass into acceleration. Now, let us do another activity to show that greater the mass, lesser is the acceleration. Here I have two toys. Here I attached two batteries, so that the mass is more, whereas here the mass is of only one battery. So, now I connected both of them with a rubber band. When I stretch, the rubber band exerts same force on both the objects. So, if I stretch and release, what should happen? Because this object has greater mass, should be accelerated lesser, whereas this object which has less mass should accelerate more. So, and I am going to release these two, the greater mass should accelerate lesser. Yeah, there it is. The greater mass will accelerate lesser, this is the greater mass, this will be accelerating less. Watch it. The one with lesser mass is accelerating more. Yeah, there it is. So, this activity demonstrates that greater is the mass, lesser is the acceleration when equal forces are applied. We will move on to Newton's third law. When one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. This can be stated in simple words as every action has equal and opposite reaction. Remember, here action and reaction means the forces. Let us do another activity. Here I have made an arrangement so that there is a balloon connected to the barrel of a pen. Now, I am going to blow it. And you see this object started moving. I am going to leave this object and see what is going to happen. This object is powered by the air inside the balloon. So, the air inside the balloon was coming out, the balloon is pushing the air out and the air which is coming out is pushing the balloon back, and thereby the cart was moving forward. Exactly the same principle will be applied in rockets. In rockets, the hot exhaust gases come out with a greater velocity and they exert an equal amount of force on the rocket, and the rocket moves up. When we walk, we are actually pushing the earth back, and thereby we get the reaction in the forward direction, and hence we move forward. We can see another example. Consider a situation where a person is on a weighing machine. He pulls an object down by means of a rope. If we observe, the weighing machine now shows less reading. This is because the person was pulling the rope down and he is applying a force downwards, and the rope applies force on the person upwards, and thereby his weight on the weighing machine is recorded less. This is because when the person pulls the rope down, the rope applies equal and opposite reaction, which results in the decrease in the reading. Whenever an object is on a ground or any place stable, its weight is acting downwards and the surface exerts equal and opposite reaction upwards. We call this as normal reaction, which will be equal to the weight of the object. Now, let us revise. Newton's first law: every object continues to remain in state of rest or uniform motion until an external unbalanced force acts on it. Newton's second law: the rate of change in the momentum of an object is directly proportional to the external unbalanced force and is in the direction of the force. Newton's third law: every action has equal and opposite reaction. So, children, now that we have understood the motion and the causes of motion and we have discussed Newton's laws, I want you people to imagine more of such situations and more of such activities which you can demonstrate various laws. Also, we are going to do more numericals in the upcoming classes. What I want you people to do is log on to SCRT website, download the worksheets and work out and show it to your teachers. Thank you.
పొద్దు పొడిస్తే కాని కాలచక్రం నడవదు, కాలచక్రం నడిస్తే గాని ప్రగతి సాగదు. యంత్రంలా చకచకా పని చేసుకుపోక తప్పదు. ప్రగతి పదంలో ఎన్నో